All right, so let's continue with our discussion of aqueous equilibria. Let's talk now about reactions involving ionization of a base. And by base here we mean the Bronsted definition of a base where, what's the Bronsted-Lowry definition of an acid-base reaction? It's a proton transfer, right? So if a base picks up a proton from a water molecule, okay, then what does it lead to? That gives you BH plus if B is neutral. And what's left behind from the water? Hydroxide, right? So a base in the Bronsted-Lowry definition is a proton acceptor. And when that base happens to accept a proton from water, it leads to the production of hydroxide, which would explain the increase in the hydroxide concentration if you put it in water. Okay, so the equilibrium constant for this type of reaction, where you have something that pulls a proton away from water to give you its conjugate acid and a hydroxide ion, the equilibrium constant for that is known as the Kb of that something, in this case, the base. Okay, so in this example right here, ammonia plus water. So your ammonia pulls a proton away from a water molecule, gives you ammonium ion and hydroxide ion. So the KEQ for this is called the Kb of NH3. Okay? So in general, when you're talking about base ionization, okay, you're talking about a reaction whose equilibrium constant is called Kb. You're talking about a reaction between the base and water leading to the formation of its conjugate acid and hydroxide. So the conjugate acid of something will just be that something with the H plus, with the proton attached to it. Okay? So ammonia with a proton attached to it would be ammonium ion. This is the conjugate base, conjugate acid of NH3. So we say that in a base ionization, the water is behaving like an acid. The water is donating the proton to the other molecule, or to the ion. Okay? So what is the conjugate acid of HCO3 minus? Let's see. So if you're asked for its conjugate acid, then that means it's behaving like a base. And what does a base do? A base is a proton acceptor. So when this base picks up a proton, what do you get? You get H2CO3. Okay? And what you get is the conjugate acid. Okay? If something accepts a proton from something else, if it accepts a proton, it forms its conjugate acid. It's behaving like a base. So what would be the reaction where the KEQ is called the Kb of HCO3 minus? So we're talking about a reaction where HCO3 minus reacts with water, and what's it doing? Since it's behaving like a base, it must be what? Accepting a proton from water. So what happens when HCO3 minus accepts a proton? It becomes H2CO3, right? And what's left behind from the water? Hydroxide. So this is the reaction we are referring to if we're talking about an equilibrium constant known as the K sub B or Kb of HCO3 minus. That's the reaction of HCO3 minus with water where it pulls a proton away from a water molecule. Okay. Solubility product. Let's talk about the equilibrium constant known as KSP. Okay. When we're dealing with very slightly soluble solids, ionic compounds in water, okay. For example, lead chloride, we say, if you remember from Chem 105, we say that's insoluble in water, if you remember your solubility rules. What that means is it doesn't really mean zero solubility. When we say something is insoluble, what we really mean is very slightly soluble, very low concentration dissolved. So for these types of reaction, okay, the equilibrium constant is known as the KSP, solubility product. Why? What would be the KEQ for this? It's going to be activity of lead ions times products, right, times activity of chloride ions squared divided by, what's the activity of a solid? 1. So the KEQ for this, you can see, is just a product of activities because your denominator is 1, right? So that's why we say, we call it KSP. SP stands for solubility product. Okay, so KSP is known as a solubility product constant. That's what KSP means. Okay? By the way, I think I didn't spend too much time with KB, huh? Let's just go back a little bit to that. What would be the expression for KB here? If I were to ask you, what is KB of bicarbonate ion? What would go in the numerator? Concentration of H2CO3 times concentration of hydroxide, and in your denominator, concentration of HCO3 minus. What's the activity of liquid water? 1. Okay. Okay, so let's look at this example right here. What would be the KEQ for, what would be the reaction whose KEQ is called the KSP of bismuth sulfide? So what would this reaction be? You're dealing with Bi2S3 solid. What happens to it in water? Ionic compound. What are the charges of the ions? Sulfide, what do you know is the charge of sulfide? Group 6A, column 16 of your periodic table, so that's -2. So what's the charge of bismuth here? And -2 times 3 is -6, so what must bismuth be? Something times 2 must be +6. So bismuth must be +3. So this gives you 2 bismuth ions with a +3 charge plus 3 sulfide ions with a -2 charge in aqueous solution. So that's the reaction. What's the expression for KSP? KSP equals products over reactants, but reactant activity of the reactant is just 1 since it's a solid, so it's just the product of the activities of the products. So what would it be? Bismuth concentration or activity raised to the power 2 times the concentration of sulfide raised to the power 3. So that's the expression for the KSP. And this is the chemical equation for it. Okay? Let's try this one. Oops, I just gave you the answer again. What's the KSP expression for bismuth sulfide? What is it? It's bismuth squared sulfide cubed, right? Okay. It's bismuth squared sulfide cubed. All right. Complex ion formation, we've already seen that with the formation of the complex ion between aluminum and water, right? That's a complex ion. In general, okay, it doesn't have to be water. In general, if you have a metal cation, it can react with nucleophiles, form coordinate covalent bond with nucleophile to form a complex ion. So for example, if you have silver ions in water, it can form covalent bonds with two ammonia molecules to give you this complex ion right here. This is called the silver diamine complex. Okay, NH3 is an example of what's called a nucleophile. Anything that has a lone pair that it can share with your metal cation would be a nucleophile. It will be seeking a positively charged center, so it's seeking a nucleus. Okay, so that's why it's called a nucleophile. So in this particular reaction, we say your ammonia is an electron pair donor. That's what we would call a base in the Lewis definition of acids and bases. Okay, so this is a more generic definition of acids and bases. The lone pair on the nitrogen is shared with the silver. There's actually a covalent bond. Okay, and we call that bond a coordinate covalent bond. So your silver ion actually forms a covalent bond with this nitrogen in your ammonia. Okay, so the lone pair of the nitrogen is actually shared with the silver. Okay, so that bond is called a coordinate covalent bond. Your silver ion, metal cation here, is an example of what's called an electrophile, an electron lover. Okay, so that's the electron pair acceptor. That's defined as the Lewis acid. Now, the formation constant would just be equal to, okay, the KEQ for this reaction, where you're forming the complex ion from the metal cation and the nucleophile. So right here, if you look at this reaction, okay, the KEQ for this reaction is called the KF of the complex ion that you made. Okay, so KF, F for formation, so K sub F is the formation constant of this complex ion, would just be this concentration of product divided by concentration of silver times, in the denominator you have concentration of NH3, and this is squared because there's a coefficient of 2 right there. Okay, so that's your expression for the formation constant of a complex ion. So CuCl4 negative 2 is a complex ion formed from copper ions and chloride ions. What is the reaction is KEQ is called the KF of CuCl4 negative 2. What kind of reaction are we talking about here? We're forming one CuCl4 with a negative 2 charge from what? From the cation, which is copper, and chloride ions, your nucleophiles, right? And how many chlorides do we need to balance this? We need 4 chlorides, so 4. Okay? So that is your reaction for the formation of CuCl4 negative 2. The KEQ for that is called the KF, or the formation constant of the tetrachlorocopper ion. Okay? So, what is the expression for KF of CuCl4 negative 2? Is it A, B, C, or D? What was our reaction again? Copper plus 4 Cl minus gives you CuCl4 2 minus. This is aqueous solution, aqueous solution, and aqueous solution. Correct answer B. Products over reactants. Yep. Good. Okay. Let's talk about determining equilibrium constants for aqueous reactions. So, simplest way is to look them up. Right? So, if you need the Ka of something, you should be able to find a table of Ka somewhere. There's one in at the back of your book. Okay, there's plenty of websites where you can find these, KB, KSP, and KF. Okay, so, and there are handbooks. Lang's handbook is a very good source. Lang's Handbook of Chemistry Okay, and it's a very, very good source of data for chemistry, and it's kind of expensive, but they sell a lot of these used on Amazon. It's really cheap. So I got a few for the lab last year. There's also the CRC Handbook of Chemistry and Physics. So for a lot of these things that we look up in this class, those are really good handbooks to have. So if you're going to be doing a lot of chemistry, that's a good thing to have, okay? You don't need a new one, just buy a used one. There's a lot of cheap used ones you can buy. Okay, so that's one way. That's the most straightforward way. The second one is just to do the experiment, okay, and you measure your activities at equilibrium, okay. Now, one thing you'll find when you do this in the lab is, remember we said when we use concentrations and partial pressures as activities, we are in a way just approximating. So there's a lot of finer details that we're not going into at this level. So chances are when you do this in the lab, in the freshman lab at least, your data is not going to be, you're not going to get very good agreement with the results you're getting compared to the literature values that you find in the handbooks, okay? And that's partly because we're making approximations when we use molarities for activities. Now, our third method is you can combine reactions with known KEQs, just like you did with Hess's law when you figured out delta H. You can do the same thing with this one. We talked about this already, except that you don't take the negative and you don't add or subtract. What happens if you flip a reaction? The equilibrium constant is just the reciprocal instead of the negative, right? And if you add two reactions, the resulting equilibrium constant is the product of the two original equilibrium constants. Another method is you can calculate it from the standard Gibbs energy of reaction. We talked about this already when we did the second and third law of thermodynamics, okay? Delta G naught, you can look that up from tables. Actually, you can calculate that from the table of delta G formation values, right? Or you can say that that's delta H reaction, delta H of reaction minus T delta S of reaction, okay? And from that, you can calculate your KEQ, okay? So KEQ will just be E to the negative delta G naught over RT. For redox reactions, we talked about this too when we had electrochemistry, and delta G, okay, is just negative N times the Faraday constant times the standard cell potential, delta G naught. And so if you know delta G naught, you can calculate KEQ. All right, so we're going to focus on, we're going to see some examples of these, okay? So that's the rest of the way. We're just going to look at specific examples. Okay, so let's take a look at these reactions. If I were to give you these reactions, what would you be looking for? Let's look at this first one. I have a reaction between HF and water, gives me H3O plus and F minus. If I were to ask you to look up the KEQ for this reaction, what table would you be looking for? What kind of constant? Ka, Kb, Kf, Ksp? Ka. Right? You're going to be looking for the Ka of HF, right? This is HF donating a proton to water. How about this second one? What would you be looking for? Ka, Kb, Ksp, or Kf? This is going to be Kb, right? This is ammonia picking up a proton from water, give you ammonium ion and hydroxide. The products give you a clue. Okay, this is forming H3O plus, so it must be behaving like an acid, whatever you added to water, and see, you'll notice, okay, this is reacting with water. How about the third one? What would you be looking at? If I wanted you to find the equilibrium constant for this reaction. Dealing with a solid, giving you ions in solution. KSP. This is the KSP of what? Of the solid, right? So you'll be looking at the KSP of copper hydroxide. So you look for tables of KSP values, look for copper hydroxide. How about this last one? What would you be looking at? What do you call this thing right here? A complex ion. So if you're dealing with the formation of a complex ion, what equilibrium constant would you be looking for? The K sub F, the formation constant of the complex ion. Okay? So you need to sort of know what type of equilibrium constant you're dealing with. All right? Otherwise it would be an easy thing to just look it up. Now, when you look up Ka equilibrium values, Ka, Kb, Ksb, oftentimes you might see it tabulated as pK. All right? So pK, that notation, when you put a p in front of a symbol, that means take the log of that and then take the negative. All right? So if you're, for example, you might be given the p. Let's say you wanted to look up the Ka of acetic acid, you might be able to find it given as pKa of 4.74. What is the Ka of acetic acid then? Then you say, all right, pKa is what? Negative log of Ka. So if I looked it up and I find it to be 4.74, what is Ka? How do I solve for Ka? I take the negative of both sides. I say log of Ka is negative 4.74. So what is Ka? Take the antilog of both sides. So Ka is 10 to the negative 4.74. Okay? And that gives me how much? I'll say 4.74, make that negative. Inverse base 10 log, okay? Inverse log. That's not what I want. I just want 10 to the x, so clear. Okay. 4.74 negative. Inverse log is 10 to the x, so 10 to the negative 4.7 is equal to 1.95 times 10 to the negative 4.74. Let me do it again. 4.74 negative, and then 10 to the x. It's 1.8 times 10 to the negative 5. Okay? So this is going to be 1.8 times 10 to the negative 5. That should be it. A note about sig figs. Okay? When you are taking the antilog, okay, the number of decimal places corresponds to the number of significant figures in the antilog. And if you're going the other way, if you're taking the log of something, then the number of significant digits in the original number must be the same as the number of decimal places in the log. So for example, if I gave you, take the log of 62.0, what would your answer be? 62, take the log, that's what? 1.79239, right? 1.79239. Now, how many sig figs how many digits should I keep in my log? This has 3 sig figs, right? So this has to have 3 decimal places. Okay? So that's how you'd round it out. Now if I were to ask you what is 10 to the 6.424, how would you do that? Antilog of 6.424. You say 6.424, antilog is just raise 10 to that power. So 10 to the 6.424, that would be 2.6546 times 10 to the 6, right? Now, I'm going the other way, so I have 3 decimal places, so I should keep 3 sig figs. So this answer should be 2.65 times 10 to the 6. Okay? Keep that in mind when you're doing sig figs. All right. Let's go into a more straightforward determination of KEQ. Just run the reaction, experimentally determine the concentration of reactants and products in the equilibrium mixture, and then you plug it into your expression for KEQ. So let's look at this simple example. Let's say you've tried to prepare a 0.1 molar solution of some acid HZ. That's a fictitious formula right there, hypothetical. So let's say you tried to make a 0.100 moles per liter solution, and you found your hydronium ion to be 0.001 at equilibrium. What's your Ka of Hz? If I'm interested in the Ka of Hz, what's the reaction I'm interested in? Hz gives me what? What's the product? H3O plus or H plus plus Z minus, right? And so what you need to do is set up an ice table here. What's the initial concentration of Hz that we have? 0.100. You know this is a this is an acid, so it's going to ionize, right? So you're going to lose, let's start off with none of the H plus and none of the Z minus. So you're going to lose X moles per liter of Hz. How much H plus are you going to make? X, right? For every mole of Hz you lose, you gain a mole of H plus and a mole of Z. So what would be your equilibrium concentrations? This is going to be 0.100 minus X. That's going to be X, and that's going to be X. So what's my Ka? What's the expression for Ka? Ka is H plus times Z minus over Hz, right? And so what would it be? It's going to be X squared, X times X over 0.100 minus X. Do I know what X is? According to this, when you did the experiment, you found the hydronium or the H plus concentration, this H plus concentration to be X, to be 0.001, and that is X, right? You found it to be 0.001, so X must be 0.001. That's what's given. So if I know what my X is, what can I do now? I can solve for Ka. How do I solve for Ka? 0.001 times 0.001 over 0.100 minus 0.001. And that gives me 0.000001 over 0.099, right? That gives me how much? 0.001 times 0.001 divided by 0.099. This is 1.01 times 10 to the negative 5th. How many sig figs should I have here? Didn't give you much. I have 1 sig fig here, so it's just 1 times 10 to the negative 5th. Okay? That's your Ka. So you can just use your stoichiometry. You set up an ice table, figure out the final concentration. If you know one of these final concentrations, you can figure out the others. So what's the final concentration of H plus? It's X, right? Z minus is X. Hz is 0.1 minus X. Let's say you tried to make a 0.2 molar solution of base B in aqueous solution, and you found the hydroxide to be 0.004 at equilibrium. What's the Kb of B? Okay, what reaction are we looking at here? Kb means what? B is behaving like a base, proton donor or acceptor? A base is a acceptor. So base plus water, it will accept a proton, gives you BH plus, and your product, other product is hydroxide. Right? So you set up your ice table again. Initially, you have 0.2 moles per liter of base. Water, you don't worry about. You have large excess of that. That's your solvent. Activity of that is 1. You have none of this and none of that. Okay. And then what would be your changes? You lose X moles of this. You make X moles of that. You make X moles of that. And what would you have at equilibrium? 0.200 minus X. And this is going to be X. And that's going to be X. What's your expression for Kb? Products of a reactants, right? So concentration of BH plus concentration of hydroxide over concentration of B. Activity of water is 1. So BH plus is X, hydroxide is X, and B is 0.2 minus X. So this is going to be X times X over 0.200 minus X. And I'm just have to plug it in. What is X? It says here hydroxide was found to be 0.004 at equilibrium. So this is 0.004. So you just plug in X equals 0.004. That gives you how much? 0.004 squared over 0.196. 0.004 minus 0.004 divided by 0.196. That's 8.2 times 10 to the negative fifth. Since I only have one sig fig here, it's 8 times 10 to the negative fifth. Okay? Okay, comment. You may be wondering, why did I say H plus was 0 to begin with? Doesn't water have H plus, like 10 to the negative 7? Right? So I'm making an assumption there that there's hardly, that 10 to the negative 7 is negligible. In fact, what do you see? How does 10 to the negative 7, which is 0.000001, compare to 0.001? It is negligible, right? So you can ignore it. Now sometimes you might not be able to ignore it, so you have to be alert to that possibility. But most of the time, this level, we don't ask you questions like that. But one thing you'll realize, though, is that this one, the fact that this Hz produces 0.001, that diminishes the H plus from water itself. Because how much H plus can water give you now? Okay, remember your H2O outer ionization gives you H plus plus hydroxide. Okay, your H plus is now at least 0.001, right? So if this water is going to give you more H plus and hydroxide, okay, it's not going to give you 10 to the negative 7 anymore. Basically, what did you do by adding that 0.001? The Chatelier's principle says you've shifted your reaction to the left. So this X is going to be significantly less than, even less than 10 to the negative 7. What's that X going to be? Well, you can find out what that is. You can say, well, 0.001 plus X, that's my H plus, right? This is my H plus. And my hydroxide is X. That would be 1.00 times 10 to the negative 14. And you see that if you solve for X there, you'll find that X is even lower than 10 to the negative 7. So once you put acids and bases in water that significantly increases the H plus or the hydroxide, you can pretty much ignore the contribution of the autoionization to the H plus and hydroxide. basically what an acid and a base does. Okay, if you add acid, you're suppressing your reaction. Okay, so Le Chatelier's principle, you're shifting your autoionization to the left. If you add more base, you're adding more product, you're shifting your autoionization to the left. So you can pretty much ignore. If you're getting concentration of H plus and hydroxide that's greater than 10 to the negative 6, you can pretty much ignore the contribution from the autoionization of water. Okay? All right. Let's say you have a saturated solution of MOH2 and you found you have hydroxide concentration of 0.0010. What's the KSP of MOH2? KSP, so what reaction are we looking for here? So MOH2 must be a solid, right? Since we're talking about its KSP. What would be the products for this? 2 hydroxides, obviously, right? So what must be the charge of your M? Plus 2. Okay? So again, you set up your ice table. Let's say you start off with an excess of this, an excess of a solid. Okay? Saturated solution. That means you have a lot of it. You have an excess at the end. And you don't worry about it because the activity is just going to be equal to 1, right? Oops. Saturated simply means that if you mix it with water, you still have some solid left behind there. So you have your M plus 2 and your hydroxide ions here, okay, in equilibrium with your solid. So you have a large excess, and the activity of that solid is equal to 1. So you don't worry about it. But if you lose X moles of this, how much M plus would you get? You get plus X moles per liter, and you start with no hydroxide. Again, we're assuming there is none, although there is some. It would be negligible. How much hydroxide would you make? It's going to be 2X, right? So plus 2X. So at equilibrium, you have X moles per liter of M plus 2X moles per liter of hydroxide. So what's our KSP expression? KSP equals M plus 2. What's M plus 2? Raised to the power 1, right? Coefficient here is 1. Times hydroxide raised to the power 2. So that's squared. And what's the activity of the solid? It's just 1. So that's just your expression for KSP. So what's our M plus? Our M plus is X. Our hydroxide is 2X. So this is going to be equal to 1. X times 2X squared. Okay? And what is how do I simplify this? What is 2X squared? 4X squared times X, so that's 4X cubed, right? Do I know X though? What information do I have here? You're told that hydroxide at equilibrium is 0.0010. So what's hydroxide? This is your hydroxide, right? This is 0.0010. So what is X? Divide by 2. So if 2X is 0.0010, X would be 0.0005. 0.268, right? So you just plug that in. You say that's equal to 4 times 0.00050 cubed. And your KSP is equal to 0.0005 raised to the power 3. This is cubed. Times 4. That's 5 times 10 to the negative 10. So 5.0 times 10 to the negative 10. Okay? That's how you solve for your KSP. Got it? So if you know what the concentrations are at equilibrium, set up your ice table and look at your equilibrium concentrations. That would allow you to solve for the extent of the reaction. X here, you can call that the extent of your reaction. Okay. So how about this one? If the solubility of bismuth sulfide in water is X, what is its KSP? Okay, recall what was the dissolution reaction? Gives you 2 bismuth ions plus 3 sulfide ions. So if the solubility means it's saturated. You've added enough so that it's saturated, right? Then that would be the concentration. What would be the KSP? Let's try to figure it out. So if I lose X moles per liter, okay, so I'm going to lose X moles per liter of that, so I'm going to make 2X moles per liter of this. And how much of this will I make? 3X moles per liter. So at equilibrium, I'll have 2X of this and 3X of that. Do we have an answer? Let's see. Oops, C and D are popular choices. Okay. KSP equals bismuth raised to what power? 2. Sulfide raised to what power? 3. And what's the concentration of bismuth? 2X raised to the power 2. What's the concentration of sulfide? 3X raised to what power? 3. You want a second chance? So let's see how we're doing this time. Okay, D is a popular answer. One more time. Who picked a different answer? Yes, what answer did you pick? Why did you pick E? Okay. 2 squared is 4 and 3 cubed is 27. The whole thing is inside the parentheses, right? So this is going to be 2 squared x squared 3 cubed x cubed. So that's equal to, this is 4 times 27, that's 108 x to the power 5. Okay, so correct answer is E. 108x to the power 5. Okay. So how do we measure H plus and hydroxide in the lab? This is one of the easier things you can do in the lab, measure H plus and hydroxide. You can use what's called a pH meter. How a pH meter works, we'll just leave that to another course. But basically, with a pH meter, you can measure the concentration of H plus, or more accurately, the activity of H plus. But at this level, we're just going to say that's the concentration of H plus. pH is defined as the negative log of the concentration of H plus. So that means H plus would be, okay, so if pH is negative log of H plus, then negative pH would be log of H plus. If I take the antilog of both sides, antilog of negative pH is 10 to the negative pH, that would be your H plus. So if you measure the pH in the lab, take its negative, take its antilog, then you get the concentration of H plus. Once you know your H plus, then you can easily calculate your hydroxide. How? Well, H plus times hydroxide must be equal to Kw, and you know Kw is 1.00 times 10 to the negative 14. So to solve for H plus, divide both sides by, solve for hydroxide, divide both sides by H plus. Okay, and so you'll find that your hydroxide is just Kw over H plus concentration. One thing you'll also find is that, here's another way of looking at it. Since H plus times hydroxide is equal to Kw, okay, if you take the log of both sides and take the negative of the log, let's just take the log first. Log of a product is equal to the sum of the logs, right? Log of H plus times log of hydroxide would be log of H plus plus log of hydroxide is equal to log of Kw. Okay. If I were to take the negative of both sides, then this would be negative of log of H plus plus negative log of hydroxide equals negative log of Kw. What did we say is our notation for the negative log of something? It's P something, right? So this is just pKw, and we call this POH, and negative log of H plus is pH. So pH and POH add up to 14. Because what's Kw? Kw is 1.00 times 10 to the negative 14 at 25 degrees. So pKw would be the negative log of 1.00 times 10 to the negative 14. Okay, so what would that be? Three significant digits. So that's 14 followed by 3 zeros. Okay, 3 decimals. So 14.000. So pH plus POH equals pKw, which is 14.000. So if I know my pH, I can solve for POH easily. All I do is subtract pH from 14. Okay? And then if I know POH, then hydroxide will just be the antilog of negative POH. So let's illustrate that with some calculations here. Let's say the pH of a solution is 4.00. Okay, what is my H plus? What's the definition of pH? Negative log of H plus. So how do I solve for H plus? pH, H plus is 10 to the negative pH. So 10 to the negative 4.00. What would that give me? That's just 1 times 10 to the negative 4, right? Okay. Negative 4. Okay, 10 to the negative 4. 1 times 10 to the negative 4. But how many seg figs should I have? 2 decimals in the pH means I need to have 2 sig figs in my answer. So it's 1.0 times 10 to the negative 4. Okay? What is my POH? pH and POH add up to 14. So it's 14.000 minus pH. So 14.000 minus 4.00, that gives me how much? 10.00. Sig fix. How do I get hydroxide? It's 10 to the negative POH. So that's 10 to the negative 10.00. So that's going to give me 1 times 10 to the negative 10. 2 decimal places, so I need 2 sig figs here. 1.0 times 10 to the negative 10. So that's my hydroxide. Okay? Now, what's another way I could have figured out my hydroxide? I could have said hydroxide equals Kw over H plus, right? So it's 1.00 times 10 to the negative 14 over 1.0 times 10 to the negative 4. That's my H plus. Same answer. I get 1.0 times 10 to the negative 10. Okay, so by measuring pH, you should be able to figure out H plus and hydroxide concentrations. And if you're doing that in the lab and the pH is not changing, then that means you are at equilibrium. You have the equilibrium values for H plus and hydroxide. Okay, so the pH scale then tells us whether your solution is acidic, basic, or neutral. What did we say? H plus and hydroxide is in a neutral solution. They're equal, right? So if they're equal, they both have to be 10 to the negative 7. So your pH and POH must both be 7 if you have a neutral solution. How do you get an acidic solution? If your pH is higher than 10 to the negative 7, what's a number that's higher than 10 to the negative 7? Example. 10 to the negative 8? That's lower, right? So 10 to the negative 5. So 10 to the negative 5 is an example of a number higher than 10 to the negative 7. What's a pH if it's 10 to the negative 5? If H plus is 10 to the negative 5, then pH is negative log of that. It's just fine. So pH less than 7, your solution is acidic. pH greater than 7, you say your solution is basic. You have more hydroxide, less H plus. Okay? So pH is lower in acidic solution. Okay? And same thing with POH. If pH is less than 7, then your POH must be greater than 7. Right? So if my pH is 5, what's my POH? pH and POH should add up to 14. So 5 plus 9 is 14. So POH would be 9. Okay. So, clicker question. pH of a solution is 4. Which of the following is true? A, the solution is basic. B, H plus is greater than hydroxide. Okay. Very good. pH 4, less than 7, acidic. So A is obviously wrong. And if it's acidic, then you have more H plus, right? Okay. This might be a good time to stop. We'll continue this tomorrow.